To understand probability, an interesting study of chance, one must first understand what a random experiment is. Let us take an example to understand this. Suppose you roll a die. One or two or up to six dots can appear on the top face of the die. Any random experiment has three basic features. It can be performed any number of times under identical conditions. Perhaps you can roll a die with your left hand on your desk, maybe 10 times or maybe 12 times. Before you roll a die, all the possible outcomes are known in advance. Like in this case, you know that you may get one or two or up to six dots. But for each roll, the actual number of dots that could appear on the top face of the die is not known. Okay, so this is an example of random experiment, a basic one, but a very good one. Now, the random experiments are very different from the experiments we know in subjects like physics. Suppose in physics, you're running an experiment to calculate the value of the acceleration due to gravity. It has a very specific outcome. Outcome is, there's only one outcome. You cannot have multiple outcomes, and then there is no randomness associated with the outcome. But whereas here we are saying that the outcome is highly random. So these are very, very different from the experiments that are done in physical sciences. Now, what is a sample space? The set of all possible outcomes is known as the sample space. So in our example, when a die is rolled, we can get one or two or up to six dots on the top face of the die. So this set can be called as the sample space. Now, if you take a subset of the sample space, we call it as a event. So for example, maybe one of the events is like getting a odd number. So that would be 135 when you roll a die. Maybe you want an even number which is less than 6. So that's the event having 2 or 4. Now, when we say a subset, empty set or the impossible set is also considered the subset of the sample space. For example, if I say that I want a 7 when I roll a die, where I know that I cannot get 7, so in such a case, getting a 7 is an impossible event or an empty set. And then if I say that I don't mind getting any number from 1 to 6, then you know that that event is going to happen. So that's the entire sample space. So the empty set and the sample space are in fact considered trivial events. Okay, another simple thing to keep in mind is if we take a subset of the sample space with just one possible outcome, we call it as an elementary event or a simple. Let us look at a few important definitions. Two or more events are mutually exclusive. If one of these events occur, then the other events will not occur. For example, if I toss a coin, if I get a head, I will not get a tail. Then if I get a tail, I will not get a head. So these two events are mutually exclusive. For another example, suppose you roll a die and then you are interested in two particular events. Event A being the set of odd numbers you get, and set or event B is a set of even numbers. Here you can either get an odd number or an even number. So these two events are mutually exclusive. Now, each event has the same chance. Let's say if you have several events and then each event has the same chance of occurring. So later on we will try and quantify this, but if you find that each of the events has the same chance of occurring, such events are called equally likely events. again, for an example, if you look at the elementary events, when you roll a die 1 to up to 6, all of them have the same chance. It's like 1 in 6. Now, events are exhaustive if a random experiment, I think it should be experiment, results in at least one of these events. Okay, so you have several events lined up, A, B, C, D, and so on. If you run this random experiment and then you see that uh, let's say there is one event which is not covered, then you cannot say that the events that you have considered are exhaustive in nature. I think the word is self-explanatory. Now, I think when we look at the classical definition of probability, things are really not that difficult. Uh, any random experiment results in, let's say, n mutually exclusive, equally likely, and exhaustive elementary events. So the stress is on the elementary events. Now, if you see that m of these elementary events favor, let's say, event E, then the probability of this event E occurring is a ratio of the favorable outcomes, which is m, divided by the possible number of outcomes, which is the, let's say you can say, the number of elements in the sample space, which is n. Now, it is obvious that the number of elementary events favoring a particular event E should be from 0 to, let's say, all the way till n. So the probability should lie between 0 and 1, both inclusive.